much for the very kind introduction. Really, you listed all my interests. Some of the field I also had some. I also gave some small contribution in another field. I gave no contribution, just very interested on them. So. And it is a big pleasure for me to be here. Well, for many reasons. First of all, because of the incredible wealth of the nature and of the culture here. It's my first time here in Malaysia, and I hope it won't be the last, because it's a really wonderful place. And moreover, from the scientific point of view, it's a great honor to be here, to give this course, this short course. So I thank Professor Zandy so much for giving me this opportunity. And if I manage to find my file, so can you help me see? Riccardo? Yeah. Okay, very good. So, can you hear me if I talk without the microphone? So it's better. For me it is better, so I'm not constrained. So I will talk about a kind of new program of research, a new research line, which is the nonlinear Schrodinger equation on graphs. I say new, but indeed this program started in the first half of the 90s by works of von Below and Ali Mehmeti and so on. But now in the last 10 years there was a huge boost, a strong boost toward the study of these topics. And in particular I will focus on an aspect which is the search for ground states for the nonlinear Schrodinger equation on graphs. And with respect to other courses here, probably this course is somewhat marginal. It is less geometric as an approach. Probably it is more analytic than, okay, thank you very much. More analytic than geometric. And so we try to be very elementary, and I probably will also do some computation on the large whiteboard and so, but it will be a very elementary computation. Please feel free to interrupt me whenever you want and to ask questions. If I know the answer, I will give you the answer, and we will think together. The choice of these topics is basically two reasons. First of all, nonlinearity appears in the title of EQuaLS8, so it is alive here. And second, and more important, for young people, PhD students and so on, I think it is good to have some insight on active research topics. And this research topic has an advantage. The advantage is that since it is at its very beginning, it is quite easy to go up to the edge very quickly. So probably at the end I will give you some hint about open problems and so on, and whoever is interested in it can talk to me, write to me, and talk to other people. And the results I will talk about are, most of them are in collaboration with my two colleagues of Politecnico di Torino, Enrico Serra and Paolo Tilli, but there are other results and other people on the side. So let me immediately give you the problem, and then I will try to motivate it and introduce it. So we have a structure here, which is a quite complicated structure. This is there is nothing special with the drawing, except that there are a lot of features and also pathologies here that can be allowed in our study. So this is what we call the graph, or metric graph, or quantum graph. I will not distinguish between these words. And also the word network is used, because in general when you are concerned with a graph, you imagine a discrete graph, though there are vertices. These points are the vertices, and then you can jump from a vertex to another. So the structure is discrete. In this case, the structure is not discrete. The structure is continuous, And this is like a circuit, if you want. These are wires and leads, and they have junctions and then bifurcates and so on and so on. So it is a continuous structure. In this continuous structure, there are two elements which are important. One element are the arcs, or bonds, or edges. So that's the intervals, segments, a half line. So these are the arcs. And when the arcs, where the arcs meet, we have the vertices. Okay? So it's a very simple structure. And there are finite arcs, like this one, for example, and also infinite arcs. So the infinite arcs start from a vertex at a finite space and go up to the infinity, so to say. So there are here, for example, there are 5 half line and the others are finite graphs. So I was mentioning pathologies because if you read a book on metric graphs, sometimes it is paying some attention on, for example, a situation like this one. Here we have 2 vertices. These 2 vertices are linked by 3 different edges. This is called a multiple connections. Okay, for us there is no problem. Multiple connections are allowed. And there are also structures like this one. So there is an arc that starts from a vertex and ends up at the same vertex. This is a so-called self-loop. And this is allowed. So it's a very general structure. Okay? And on this structure, we define this functional. Okay? Is it sufficiently large? Okay, can you read from the last line here? This is called E, and it is an expression of the energy, some energy. And okay, there are many possibilities. Definition of energy depends on the system you are considering and what you are modeling with a structure like that. But we will focus on a particular choice of the energy, which is quite simple, quite popular, but however, it is not trivial at all. So this energy is the sum of 2 terms. The first term is a typical quantum kinetic term. So we have a gradient or a derivative of a wave function u, and we compute the L2 norm of this derivative, and we take the second part. So this is kinetic energy. And then there is a so-called nonlinear term, or better, non-quadratic term, which is this one. Here there is a minus sign. Minus sign means that this is a negative contribution to the energy, and dynamically this corresponds to a focusing action. Okay? So, indeed, this is the energy associated to a focusing nonlinear Schrodinger equation. Then there is a coefficient, just because it is comfortable to have here one of nothing important. And here we have the L2 norm to the 5th power. So let me remember, let me recall what I mean. I just mean when I write something like that, I just mean an integral of the 5th power on some space in general in the graph. Okay? I will be more precise with this definition in the next lecture. This is just an intuitive slide in order to understand what we are doing. So, and we have a limitation on the power p of the nonlinear term. P is between 2 and 6. Okay, it's between 2 and 6. Okay, p equal to 2, we are in the linear case where the energy is quadratic. So it is standard, I don't want to treat this case. And p equal to 6 is the so-called critical case. And we will try to give some hint of what happens in the critical case. But in general, when studying the nonlinear Schrodinger energy, or the nonlinear Schrodinger equation in one dimension, p equal to 6 is a complicated problem from many points of view. Okay, so at least for the first lecture, we will limit ourselves with nonlinearities whose power is between 2 and 6. What is the problem? The problem is the easiest, the simplest, the first variational problem you have with the structure. So, among the continuous function, what does it mean? We will define it properly, but just intuitive ideas. These are bonds, and then you can define a function for any point of the graph. Okay? Complex value, for instance. Complex value function. Continuous means that it is continuous inside the edges, but also at vertices. If you go to this vertex from 2 different edges, at the end point, at the vertex, you will find the same limit. You will find the same. Okay? among the continuous function with the same mass. Mass here means the L2 norm, okay, the same mass mu. We wonder whether there exists a minimizer of the energy. And this is what we call the nonlinear ground state. Okay. So, first observation, very, very elementary. Without this constraint, without the mass constraint, minimizer cannot exist. Is it clear? Why can't it exist? Because if you let the mass free to vary for all positive values, consider the function lambda u, for example. You fix some u and consider the function lambda u. Then you have that the energy E lambda ug scales probably here, but in any case it is quite easy. Let me use this iron rod. In the energy you have the first kinetic term that is quadratic, so here you have lambda squared over 2, and the second term is more than quadratic, so you have lambda to some power p. See, so you don't have any mass constraint, so you can let this lambda go up to infinity. You can push it to infinity, and this grows quadratically. This grows more than quadratically, so what you find is that for lambda that goes to infinity, the energy goes to minus infinity. So the energy is not lower bound. You cannot have a minimizer. This is why, from a mathematical point of view, why we had a mass constraint. And there are also physical reasons in order to add a mass constraint. So the problem is not what is the ground state. The problem is simply the existence or the non-existence of the ground state. The answer will be quite complicated, as we will see. The problem is not closed. So there are some graphs for which it is quite difficult to understand whether there is a ground state or not. But in any case, the answer will depend on the topology of the graph. Topology means it is not important which are the lengths of the edges. That's the topology, the shape, the general shape of the graph. But sometimes topology is not sufficient, and in this case it's the metric. So the exact length of the edges will be important in order to find the ground state, the existence of the existence. So this is the problem, okay, the problem I will treat in these lectures, and why this problem can be interesting from a physical point of view. So here I have stolen this slide from Ketterle, from Wolfgang Ketterle's website. Probably most of you already know this picture, which is very famous. Ketterle presented it in 2001 at his Nobel lecture when he was awarded Nobel Prize for having realized the first or the second Bose-Einstein condensate. And this is a very clear explanation, of course not very detailed, but a clear explanation of what is a Bose-Einstein condensate. And starting from this picture displays a gas of particles, these red balls, at high temperature T. So if the temperature is quite high, then the behavior is very simple. They are like billiard balls. So think, for example, of a classical Boltzmann equation. You have these balls that go through straight lines and they hit each other and so on. And the overall effect is a thermalization. But when temperature goes lower and lower, at some point the quantum nature of the particle becomes important. And since you have the de Broglie wavelength, which is proportional to the inverse of the square root of the temperature, this wavelength becomes larger and larger. At some point you start considering, you have to consider not the particle as particles, but as waves, wave packets like that. Or you can also argue that the interference phenomena become important when the temperature is quite low. And then, if temperature becomes lower and lower, you reach a critical value of the temperature, which typically some fraction of Kelvin, or some 2 or 3 Kelvin. And there is a transition, there is a phase transition. Some of the particles collapse to the same quantum state. So there is a wave function here, and the wave function tends to occupy the whole box, the whole track where the gas is confined. And there are also other particles, they are not collapsing in this giant wave function. But if the temperature goes to zero, then all particles lie in the same quantum state. So there are basically two phenomena which are interesting. First of all, every particle acquires a wave function. Of course, in general, for quantum system, this is not the case. Interacting particles don't have a single wave, don't have an elementary wave function. But when t goes to zero here, all particles have a wave function, and second fact, the wave function is the same for every particle, and it is called the giant metal wave state of the Bose-Einstein condensation. Of course, there is some literature, of course, the classical works by Bose and Einstein, and then here the first of the two works for which Nobel Prize was assigned in 2001. I already cited Kepler, and here there is the other work of the group by Wieman and Cornell, 95. And the second one is the work by Kepler. And so these are the experimental results. So these are the old ideas Bose-Einstein. Here are the experimental results, and here there are the theoretical results. This is a book by Vitalievsky and Stringari, the group of Trento, which is very active on these topics. And the difference from the first two works, if you want, and 8 years later, the works by Vitalievsky and Stringari, is that here the derivation of the condensation by Bose and Einstein was made considering non-interacting gases. Basically, particles are free. But here, interactive particles are considered, and there is also a pioneeristic, not only pioneeristic, and this is the mathematical breakthrough where Bose-Einstein condensation was proved rigorously by Lieb, basically by Lieb and Schrodinger, and there is this book by Lieb and Schrodinger. This is just for an overview. And the work by Lieb, Schrodinger, and so on is based on a variational problem, of course. And so let me give you the very basics about Bose-Einstein condensate. So again, we have this gas of identical bosons at very, very low temperature, and in order to realize it, you have to construct a trap in which the system is constructed. The trap is constructed by using some magnetic or optical stuff, and at the end you find that all particles or almost all particles lie in the same quantum state phi, and mathematically phi solves this variational problem. You have to minimize an energy functional among all functions in H1 of the trap, on the shape of the trap, with some normalization laws, which is sometimes taken to be not the L2 norm of the function is equal to 1, but is equal to n. Because here the interpretation is that the integral of u squared over some region gives the number of particles that you can find in that region. And the functional is a nonlinear energy, like the one I showed you in the first slide. So you have a gradient of so kinetic term, gradient of the function on the trap, and then there is a fourth power, okay? And in the functional I'm going to study, instead of 4, I put some p, so in some sense mathematically I'm generalizing the problem here. And I put also a minus sign here, and here the sign is given by this alpha. Notice that alpha is the only mark of the interaction between the particle of the gas. Technically, it is the scattering length of the two-bond interaction. It can be both positive and negative. Okay? In the last 10 years, in the laboratory of Cornell in Colorado, Beeman and Cornell in Boulder, Colorado, they studied this attractive gas for constructing Bose-Einstein condensation. So there is a focus in for this Bose-Einstein condensation. And in the last 10 years also, there were a lot of technological improvements concerning the shape of the trap in which to confine the condensate. So at the beginning, traps were basically ellipsoidal. It was the easiest shape to realize. And now there are also some almost two-dimensional traps. There are the so-called disc-shaped condensates and also elongated traps. And there are the cigar-shaped or tube-shaped condensates. And in the last 2 years, some works appeared about branched traps. Branched traps means traps made of several edges. Of course, our mathematical problem can be seen as to be related to these topics. Finding the state of a Bose-Einstein condensate in a branched trap. Particular hypothesis of that. Yeah.
Is it like UX to the four with like the interaction Lagrangian, something like that, and alpha is the coupling?
Okay, I will give you some hint on how to rigorously derive this term. But the idea is that this fourth power is a sort of resulting of all the interaction that a single particle feels from the presence of the other particles. It's a sort of mean field made for a single particle considering the field of the other. This is the idea. And there are some scaling limit, and then this alpha results from this sort of average. I will give some hint about that. Of course, there are other physical motivation in order to consider dynamics and variational properties on traps. In all situations in which one direction is more important than the others, of course one can imagine to squeeze the three-dimensional structure in order to end up with a branch that will unify the structure, and there are many works. In particular, to my knowledge, the first people to propose the study of a Schrodinger equation on a graph were Riccardo and Scher. And they are physicists studying chemistry, for example the chemistry of the I don't know how to this is the Italian benzene of the benzene, so this is the basic structure of that molecules. The idea of Gutenberg, the idea was by Linus Pauling in 51. The idea was to consider the valence electron as being wave packets moving in the string. Valence electron were moving through the molecules. So the idea was consider this ring as a sequence of edges and write down a Schrodinger equation for a wave packet moving. This program was fulfilled by Gutenberg and Scher in 1953. There was a very interesting and very heavy paper, which is a sort of milestone on this. And then there are many other studies. There are some studies in the last 2 years, in particular by Kashakwati, Finkonoy, and Pelinovsky, and Shaikova, and other people this year published some very interesting thing about Schrodinger dynamics and ramified structures. And now I go more deeply to your question. So everybody here knows that quantum mechanics is a linear theory. Schrodinger equation is a linear equation, and so the problem is how to pass from a linear to a nonlinear dynamics. How to justify this fourth power in the Bose-Einstein condensation energy. And there is a long history here. I will give you a result of myself together with Francois Goltz and Alessandro Teta. This is nowadays it is not the most important result. I will cite much deeper and interesting result than ours, but it was at least the first derivation of the nonlinear dynamics, of the cubic dynamics starting from the nonlinear one. And it is a long story. From a mathematical point of view, it starts in 74 and then went through several papers and several techniques. I just give you some hint. HEP formulates basically a conjecture on this possibility to go to a nonlinear dynamics from a linear one, but studying another problem, which was the classical limit. And then Schroedinger and Velo, some years later, passed to the second quantized formalism. Here you are much more expert than me, second quantized formalism. And they used not the cubic equation, but the Hartley equation, which means, now I'm going to time-dependent equation. Hartley equation is this one. You have the time evolution generated by a Laplacian, and then you have a nonlinear term, which is a convolution of the potential and the modulus square of the wave function. This is Hartley equation, which is easier to deduce than the cubic Schrodinger equation. And then, in the first quantized formalism, there was this important result by Riccardo. We are in the 80s, and after 20 years more or less of silence, there were new methods, first by the French school, Bartos, Goltz, Mausa, and then the first very important result was given by Erdős and Yao, and they were able to deduce the Hartley equation, where in the case in which V is a Coulomb potential, so there is a singularity. It was not easy at all. And then here we started with Bartos, Goltz, we started to study the problem in which basically V is a Dirac delta. If V can be considered a Dirac delta, then Dirac delta is the identity for convolution. What we would find at the end is this one. This is a much more singular limit than the other. So in order to give you the flavor of this problem of passing from linear to nonlinear dynamics, I will, okay, sorry, here there is the other part of the story. The other part of the story is still very open, and the turning point is here. This work by Rodniansky and Schlein in 2009. They came back to the second quantized formalism, but for the first time they were able to use it in order to obtain good estimate on the fluctuations. Okay, there are fluctuations, there are errors when passing one linear to nonlinear dynamics, and they were able to estimate. And at some point, at this point, the competition became to a good estimate on the fluctuation. There is another important paper by Peter Pickler, who found another completely new and simple techniques in order to do the same thing. But now I think the problem is basically closed in the sense that technically, with the techniques developed by Benjamin Schlein and his group in Zurich, basically they got the best possible fluctuation. But you see, there are still some works, new models, and so on. So the story is very open. But the simple result I wanted to show you here is our result in 2007, which is one-dimensional, so it's quite adaptable to graphs. Graphs are quite one-dimensional. So and this is the problem. We have the n-particle gas, okay? One-dimensional n-particle gas of quantum particles, and here you have that the time evolution is generated by an operator which has a kinetic term, so Laplacian sin n, plus a potential term. Okay. Potential term is strange because the potential here depends on the number of particles. We consider quite strange. How is it possible that a potential depends on the number of particles? Of course, when bosons are there, they don't count each other in order to understand how strong the are. But it has a meaning. I will come back to it. So, This is a so this is a rescaled potential, and let me explain you why it is rescaled in this strange way. So instead of having a potential V of a, depending on the distance between two particles, x, y, and x, y minus xj, this is the distance, we have something like that. N to some power gamma, gamma is positive. So when n grows, this potential is okay, and becoming polar. So it is going to a Dirac delta. But then we have n to the minus 1, n to the gamma minus 1. So we have another n, a denominator, and this means since gamma is less than 1, this potential is becoming lower and lower and more concentrated. So this scaling, so this dependence of the potential on n, is the result of two different scaling. One is a weak coupling because as n grows, the coupling constant goes to 0. The second is a short range. So as n grows, the potential becomes more and more concentrated. Okay? So in order to obtain this kind of nonlinearity as a limit, as a scaling limit, we always have to mix these two ingredients, weak coupling and short range. Then we start from a factorized state. So we suppose that at the beginning the system is already condensated. There is the fact that every particle has a wave function phi, and phi is equal for all particles. Okay? But this is the initial data, these are the initial data, this is the time evolution. But as the time goes by, immediately the interaction here destroys the factorization. Okay? If you start from factorized state and then you let particle interact, factorization is lost. The content of the theorem is that in some technical sense, when n goes to infinity, so this V tends to disappear because it becomes concentrated and low. As n goes to infinity, the factorization in some sense is restored. But it is not restored in the sense that the evolution is free, the limit evolution is free. The limit evolution becomes nonlinear. I go slower here. So start from this Cauchy problem. And here there is some technical hypothesis. There is also a mistake because this psi n is not here. In any case, start from a Cauchy problem with a regular phi. The content of this hypothesis is just that phi must be enough regular. Then consider the so-called marginal or correlation function, which is nothing but the density matrix of the one particle state. If you have one particle, then its state is not given by a wave function, but instead of a wave function, you have an integral operator, if you want. This is the solution psi n of this problem. This is the solution psi n. Multiply psi n by its complex conjugate, then the first variable, the first space variable x and y here of the psi n is left untouched. But the other variables are equaled one by one. Here we have x2 up to xn and so on. And all that variables must be integrated out. x2, xn. This is just taking a marginal in a probability theory. And what happens is that at the end you have a function of the the variables of only the first part. This is the state of a one particle. Remember, one particle in a gas does not have any wave function. It has a density matrix, and this is the entry density. So the content of the theorem is that when n goes to infinity, this density matrix becomes factorial. And it is the integral kernel of an orthogonal projection on a function phi. And this function phi evolves non-linearly, exactly with a cubic Schrodinger equation. This is I don't know if it is more clear now. So there is a quite technical and complicated limit here, and I also had prepared some slide about the proof of that, but probably it is a bit sideways, and I don't want to insist on that. I only want to tell you what is the meaning of this, what is the interpretation of the fact that heat depends on merit. The interpretation of the fact that heat depends on merit is the following. Of course, the physical potential does not depend on the number of particles that interact. But putting this n in this way and pushing it to infinity means that for a very large n, the approximation we are making, okay, we are almost at the limit. And when n is large, this means then the potential is very low and very concentrated. So again, the meaning of this scaling again is that we are considering a weak coupling regime and a short term distribution. Okay, this is just to try to give you a message about this passage from the linear to the non-linear regime. It is very implicated. If you look this paper or worse, still worse, the following ones, you will find that papers are very technical. I don't want to insist on that. Now I want to pass really, I want to start with the topics of the course and consider the first very simple case, the case where the graph is the real line. So remember, the problem was the following. Fix a mass constraint. So fix a value of the mass mu greater than 0 and minimize the energy given by this kinetic term and the focusing on linear term, like that, with p strictly between 2 and 6. So the minimizer of these energies with this constraint exists for any value of mu, and it is given by the family of the solitons. The solitons can be written in this way for everything. Very old result. Okay. Here it is not written what happens in the case equal to 4, so it is done. But we will see the case and equal to 4 probably more closely, because I would like to develop the argument for the case of the line and p equal to 4 in a quite explicit way. Just deriving this shape of the minimizer, which will be very important for the problem of the graphs. So the course, the real course starts here. So just a preliminary observation is the following. So as quantum guys, you all are used to deal with complex value functions. Okay? For this kind of problem, it is not necessary to consider u as being complex value. It is sufficient to consider u real valued, but also less non-negative. It is sufficient to consider u non-negative, because this inequality holds the energy of the absolute value of u when we consider as a graph the real line, instead of a graph, a real line, is less or equal than the energy of u on the line. Okay? So the minimizer must be a non-negative function. And it is quite easy to understand why. And if u of x is a phase e to the I theta of x modulus of u, then simply differentiate it, and you have that u prime of x will be equal to e theta prime of x, and then e to the I theta of x modulus of u of x plus e to the I theta of x modulus of u of x prime. Okay, so very elementary. Now just notice that the first term is imaginary, the second term is real. So if I take the modulus of u prime if I take the modulus of u prime, let me do it to the second power, it will be the sum of the second power of the two terms. So we have theta prime second power, then the phase here does not count, we have u of x to the second power plus u of x prime after the modulus to the second power. And this is greater or equal to the second u of x prime to the second power. So this means that when I integrate, when I compute the kinetic energy associated to u, this will be greater or equal than the kinetic energy associated to the modulus of u. This is a general inequality. It's quite important in this sort of. So for what concerns the kinetic energy, we have that the kinetic energy of modulus of u is less or equal to the kinetic energy of u. For what concerns the nonlinear energy, there is no difference, because when I take u of x to the pth power, that means e for the dx, we are sufficiently old in order to speak to this formal stuff. This is equal to u of x, and then I will have to take a second module, but the second module is useless here in this case. So, when passing from u to modulus of u, the kinetic energy decreases, the nonlinear energy remains the same, so this inequality is true. And this allows us, in order to consider only non-negative function in our variational problem. Okay, from here, it is quite clear that here we have, okay, I'll let in front of you. It is quite clear that here we have equality if and only if theta prime of x is equal to 0 for every x. Okay. Now, one would like to conclude that this is true if and only if theta is constant for every x. But this is not really true. So as an exercise, because this is a spool, so I can suggest you some exercise, of course. You are not obliged to think about it. And I can give you the following exercise. Find u equal to e to the I theta modulus of u, such that it's easy, don't worry about that. The energy of the modulus of u is equal to the energy of u, and the theta is not constant. Even though this must be. It's easy. It's just my perverse way of talking that makes it because okay, so we can restrict to non-negative functions. This is the first. The second point concerns the existence of a minimizer. Okay. Thank you. Next time we will be able to do this. So the second point concerns the existence of a minimizer. So in order to do that, there is a very well-known techniques in functional analysis. Does somebody knows what is this techniques? I just have some questions, not to judge, but only to understand what I can take for granted and what I cannot. So, does anybody know how to deduce the existence of minimizers for this problem using a precise technique of functional analysis? The name of the technique, the name of the guy who developed these techniques. Okay, I'll tell you in any case I won't explain this technique. One is the concentration compactness. I will try to skip using it in this lecture. Okay. If at some point it turns out to be unavoidable, that I will use it. But in principle, I would not like to do it, and this is mainly due to reactive idioms. And there are also contributions by Kasnat, actually, So, I won't talk about that, but the message here is that a general theory states that a minimizer exists here. Okay? And now knowing that a minimizer exists, we would like to deduce its shape. So the third point is the expression of the minimizer. For P equal to 4. I will lose some time in order to find the exact shape of the minimizer because it will be useful on what is coming next. So I will, for the rest of this lecture, I will concentrate on the case of the line and probably also for the first part of the second lecture this afternoon. The expression of a minimizer can be found by solving a differential equation. By solving the differential equation, and this can be quite unclear because the problem here is minimizing a functional, so evaluating a function on many functions and take the good one, the minimizer. But now I'm telling you that this can be made by solving a differential equation. So I ask you, does somebody know why, or which are the names, very old names, that are invoked in order to justify this passage from the functional and the differential equation? take phi, a function in h1 of r, or also more regular, it is not important, and consider t in r, and consider this difference of the energy evaluated in u plus t phi minus the energy evaluated at t. We are in R, and we consider the case P equal to 4. Because there is some magic associated with P equal to 4. This you know. You know, P equal to 4, there is some magic, which is called integrability. And for us, the use of the integrability is very, very elementary. We just use it in order to do exact computation. Nothing more. However, here you have first a kinetic term. So instead of the prime, I will use the point for the prime derivative. Okay? Is it good? It's a derivative with respect to x. But it is more comfortable to use. So this is the kinetic term associated with the first energy, and then we have the nonlinear term associated with the first energy, u plus dphi to the fourth power, and then we have to subtract the energy of u minus 1 over p u to the 4. Okay? So here cubic it is very simple because we can compute the because we can explicitly compute the fourth power. So you take the first term here and just develop the square, the second term develop the fourth term, and you see that here the square of u dot is cancelled by the square of the u dot of the second term, and also here the fourth power of u. So what we find at the end is that this difference between the energy on u plus t phi minus the energy on u is equal to, here there is a t and then u dot phi dot. And then there is another term which is linear in t. Here, sorry, I put here p, but p is equal to 4. Okay. So here the fourth power gives u to the fourth plus 4 times t u to the cube t. So we have t u to the cube t. And then there are the other terms. So you have plus t squared, the integral of phi dot square, and then minus 3/2 t squared, u squared, t squared, and minus t to the third power, u t to the third power, minus t4 over 4 t to the fourth power. So this is a function of t. Okay? This is a function of t. Now, if u is a minimizer, then this quantity must be greater or equal than 0. Okay? But in t equal to 0, this quantity is exactly 0 because it's a e of u minus e of u. So, u is a minimizer implies that t is a minimum point for the function f. And since, sorry, t equal to 0 is a minimum point for the function f, so f prime of 0 must be equal to 0. And f prime of 0 is nothing but is given by the first two terms. Okay, when you take the derivative, you divide by t, and then push t to 0, and if you divide by t the other terms, there is still some t remaining there, so all these terms don't count. Here, f prime of 0 is given by the integral of u dot phi dot minus u to the third power of phi. Okay? And this is what is called the variational gradient or the variational derivative of E. But this will be true for a free problem. Okay. In this case, the problem is constrained. Okay. Now, take the analogy of the reduction from the functional E to the function f. Okay. From analysis 1, we know if f has a minimum point, then the derivative must be equal to 0. And push this analysis to the case of constrained functions. I'm sure you all know what you have to do when you have to solve a problem of minimizing a constrained function. What is the name here in the theorem? It's a guy who came from my town. Riccardo. Yeah. He was a guy from Turin. Then he went to Berlin and then to Paris.
He was not French.
No. He spoke a very awful French. The French students were complaining about his very strong Italian accent. So, this is if f is constrained, for example, the problem of minimizing f among all points x such that g of x is equal to 0, then the condition is not simply that the gradient of f, or the prime derivative of f, sorry, here x is a vectorial function, but it's not important. The condition is no longer that the gradient of f must be equal to 0, but the condition is that by Lagrange multiplier theory, the gradient of f must be proportional to the gradient of the constraint g. Let me write it with a minus sign that will be comfortable in the second half. But I write it here. And may I take just 2 minutes? Thank you very much. The idea is the following. If you are in the plane and you have to minimize a function along a curve, then it is not necessary that the gradient of the function is 0, but it is sufficient that the gradient of the function has no projection along the curve. So when going through the curve, here basically the first variation of the function is 0. And being orthogonal to the curve means being parallel to the gradient of the function g that defines the curve. The curve is a level set for g, so the gradient of g is orthogonal to the curve, and in order to have an extremal point, also the gradient of the function must be orthogonal to the curve. This is the reason why gradient of f must be proportional to gradient of G. This is the function and this is the constraint. And this is also true for functional, and here I really finish. For functional, we have that gradient of the energy is equal to minus lambda gradient of G, where G for us is the mass constraint. The integral of u squared minus mu is equal to 0. And we compute the gradient of E, and the gradient of E was given by this expression. The gradient of E on phi is u dot phi dot is minus u cube phi. This has to be equal to minus lambda. If you compute the derivative of G as we did before, this is just minus lambda u. And so in the second lecture we will start from this equality. We will derive a differential equation, we will solve it, and we will find the family of solitons in the particular case P is equal to 4, and this is the very starting point in order to face the problem on graphs. Okay? Thank you very much, and sorry for being a bit late.